Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The publication of Leonhard Euler's 1736 masterpiece, Mechanica, sive motor scientia analytis exposita, represents a pivotal moment in the history of science. It stands as a profound declaration of intent, a two-volume treatise dedicated to the systematic reformulation of the entire science of motion, transforming it from the geometrical demonstrations of Isaac Newton into the powerful, universal language of algebraic analysis. This essay undertakes a direct and critical evaluation of the Mechanica's internal claims, arguments, and specific methodologies. It follows the work's intellectual progression, section by section, to assess the validity and coherence of Euler's ambitious project as he himself laid it out. The purpose here is to examine the work on its own terms, scrutinizing the logical architecture and conceptual machinery that Euler constructed to build a new foundation for mechanics, one that would ultimately shape the development of mathematical physics for generations to come. Section 1, the foundational axioms, and the analytical mandate. The Mechanica commences with a clear statement of its philosophical and methodological commitments. Euler's primary claim in the introductory chapters is that the science of motion is amenable to a complete and rigorous exposition through the calculus, deriving all its truths from a few self-evident first principles. He posits that mechanics can achieve the certainty of geometry while possessing the operational power of algebra. In evaluating this foundational claim, one must examine his initial definitions and axioms. Euler defines a body by its mass, which he conceives in a Newtonian sense as the quantity of matter, and the state of a body by its position and velocity. His central innovation is the formulation of the fundamental principle of dynamics as a differential equation. He posits that the infinitesimal change in velocity is directly proportional to the product of the motive force and the infinitesimal element of time, and inversely proportional to the mass of the body. In the symbolic language of his time, this relationship would be expressed such that the differential of the velocity equals the force divided by the mass, multiplied by the differential of time. This formulation is the analytical core of the entire treatise. His claim for its primacy is validated by its sheer utility throughout the subsequent chapters. By expressing the core law of motion in this differential form, Euler provides a universal engine for solving problems, a stark contrast to the bespoke geometric constructions required for each problem in the Principia. The internal coherence of his project rests upon the successful and repeated application of this single analytical principle to an ever-expanding domain of physical phenomena. His initial chapters thus serve as a successful manifesto, establishing a framework whose power is demonstrated, claim by claim. In the remainder of Section 2, the efficacy of analysis in rectilinear motion following the establishment of his core axiom, Euler immediately applies it to the study of a mass point moving in a straight line. The central claim of this section is that his analytical method can systematically and exhaustively solve the motion of a particle under any conceivable force law, provided that force depends only on the particle's position. He begins with the simplest case, a constant force, such as that exerted by gravity near the Earth's surface. By integrating his fundamental differential equation twice with respect to time, he derives with algebraic simplicity the familiar laws of uniformly accelerated motion, yielding equations for velocity and position as functions of time. He then proceeds to more complex and significant cases. He investigates a force proportional to the distance from a central point, setting up the differential equation whose solution yields simple harmonic motion, which he correctly identifies and solves using trigonometric functions. Subsequently, he tackles the astronomically crucial case of an inverse square force law. In each instance, Euler's method is identical. Formulate the specific force law, insert it into the universal differential equation of motion, and perform the necessary integrations to find the velocity and position. The evaluation of this section's claim is overwhelmingly positive. Euler demonstrates that his analytical machine works flawlessly for these foundational problems. The method's power lies in its uniformity. It reduces the physical problem to a purely mathematical one of solving a differential equation. This process is algorithmic and general, fulfilling his promise to create a science of motion that is both rational and operational. The success in these varied cases of rectilinear motion provides the first substantial proof of concept for the entire Euler program. Section 3 Analytical Dominion over Motion in Resisting Media. Euler next expands his inquiry to a domain that severely tests the limits of pre-analytical methods, the motion of a body through a resisting medium. The implicit claim of this extensive section is that the analytical framework is robust enough to incorporate complex, real-world phenomena like friction and air drag, which are computationally prohibitive for purely geometric approaches. Euler models the resistive force as a function of the body's velocity, considering cases where resistance is proportional to the velocity, to the square of the velocity, or to a combination of such terms. This introduces a velocity-dependent term into his fundamental equation of motion, fundamentally altering the character of the required integrations. For example, when analyzing vertical motion under gravity with a linear drag force, the resulting differential equation leads to solutions involving exponential functions, correctly predicting the existence of a terminal velocity where the force of gravity and the force of resistance achieve equilibrium. When examining resistance proportional to the square of the velocity, the solutions involve logarithmic and hyperbolic functions. In evaluating this section, one observes the profound extensibility of Euler's method. The internal logic is impeccable. The physical hypothesis about the nature of resistance is translated directly into a mathematical term, and the analytical machinery proceeds to generate a solution. This section is a powerful demonstration of the superiority of his approach in terms of scope and practicality. It moves mechanics from an idealized realm into one that can grapple with the complexities of empirical reality. The successful and detailed treatment of these problems serves as a compelling argument that his analytical science is not merely a reformulation but a significant expansion of the domain of soluble problems in dynamics. Section 4 The orthogonal decomposition of curvilinear motion. The first volume of the Mechanica culminates in the analysis of the unconstrained motion of a mass point along the curve in a plane or in space. The critical claim advanced here is that the principle of motion can be generalized from one to multiple dimensions by decomposing the motion and forces into orthogonal components. This is perhaps Euler's most significant and lasting methodological contribution within the work. He introduces a fixed coordinate system, implicitly Cartesian, and asserts that the general differential equation of motion can be applied independently along each axis. The second time derivative of the x-coordinate of the particle is determined solely by the x-component of the total force, and the second time derivative of the y-coordinate is determined by the y-component of the force. This technique effectively transforms a single complex problem of curvilinear motion into a system of 2 or 3 simpler problems of rectilinear motion. He applies this method with great effect to the classic problem of projectile motion under uniform gravity. Deriving the parabolic trajectory with analytical elegance, he then applies it to the far more challenging problem of central force motion, including the inverse square law of planetary orbits. By resolving the forces and motion in a coordinate system, he rederives Kepler's laws of planetary motion from first principles. The evaluation of this claim is that it is a resounding success and represents the true heart of analytical mechanics. The technique of orthogonal decomposition is a tool of immense power and generality, forming the bedrock of vector mechanics today. Its introduction in the Mechanica makes a compelling case for the necessity of an analytical viewpoint. The very idea of resolving a vector into components is inherently algebraic and analytical, and its success here vindicates Euler's entire project of moving the science away from synthetic geometry. Section 5. The introduction of constrained forces. For motion on a curve, the second volume of the Mechanica addresses a new and profound challenge, the motion of a particle that is constrained to move along a given curve. The central claim of this section is that the principles of dynamics can be adapted to handle such constraints, while introducing the concept of a reaction force exerted by the curve itself. This is a monumental conceptual leap. Euler's method involves a masterful blend of physical intuition and analytical rigor. He argues that for a particle moving on a prescribed curve, like a bead on a wire, the external forces acting on the particle can be decomposed into two components, one tangential to the curve and one normal to it. He posits that the tangential component of the force is responsible for the change in the particle's speed along the curve, governed by his familiar equation of motion applied along the arc length. The normal component of the external force, he claims, is perfectly balanced by a force of constraint exerted by the curve on the particle. This constrained force is always directed perpendicular to the path and performs no work, its sole function being to keep the particle on its prescribed trajectory. In evaluating this claim, Euler's reasoning is profoundly insightful. He effectively reduces a 2- or 3-dimensional problem of constrained motion to a 1-dimensional problem of unconstrained motion along the curve's arc length, with the added task of calculating the required normal force. He applies this method to solve classic problems like the motion of a simple pendulum and determining the trajectory of a particle sliding down a given curve. This section demonstrates the maturation of his framework, showing it can handle not just free motion but also systems subject to explicit geometric limitations. The introduction of the normal force of constraint is a brilliant device that preserves the integrity of his analytical system, while extending its reach into a vast new class of mechanical problems. Section 6. The generalization of constraints to motion on a surface. In the final major analytical section of the Mechanica, Euler takes his framework to its highest level of complexity, addressing the motion of a particle constrained to a given 2-dimensional surface. The claim here is that the method of decomposing forces and introducing a force of constraint, developed for curves, can be generalized to the more difficult case of surfaces. Here, the particle possesses 2 degrees of freedom for its movement on the surface. Euler's approach is a direct extension of his previous logic. He decomposes the applied external forces into a component lying in the tangent plane of the surface and a component normal to the surface. He asserts that the component in the tangent plane dictates the particle's acceleration on the surface, while the normal component of the force is precisely counteracted by the constrained force exerted by the surface. This constrained force, directed along the surface normal, ensures the particle never leaves the surface. The evaluation of this section reveals both the power and the practical limitations of Euler's method. In principle, his claim holds the physics is sound and the analytical procedure is logically coherent. He has successfully defined the general method for solving any problem of motion on a surface. However, the execution of this method for all but the simplest surfaces, like a plane or a sphere, becomes extraordinarily difficult. The required differential geometry, describing the surface and the particle's path upon it, leads to systems of differential equations that were immensely challenging to solve with the mathematical tools of the 1730s. This section, while a conceptual triumph, also highlights the computational friction inherent in his direct, force-based approach. It is here that one can perceive the intellectual pressures that would eventually lead his successor, Joseph Louis Lagrange, to develop a more abstract, energy-based formalism that handles constraints with greater algebraic elegance. Euler's method is correct and foundational, but its application in these most general cases reveals its own inherent complexity, paving the way for future innovation. In conclusion, a direct evaluation of the internal claims of Euler's Mechanica reveals a work of extraordinary coherence and success. Section by section, Euler systematically validates his initial thesis that the entirety of mechanics can be derived from a handful of principles expressed in the language of differential equations. From the elementary cases of rectilinear motion to the complex scenarios of motion in resisting media, his uniform analytical procedure proves its efficacy and generality. His introduction of orthogonal decomposition for curvilinear motion provided the essential toolkit for all subsequent mathematical physics. Furthermore, his brilliant treatment of constrained motion, through the conceptual introduction of forces of constraint, dramatically expanded the domain of solvable problems to include particles on curves and surfaces. The Mechanica is more than a mere translation of Newtonian ideas into a new notation. It is a fundamental reimagining of what mechanics is and how it should be done. It established a paradigm of practice, a universal algorithm for turning physical problems into mathematical ones, while the final sections on surface motion hint at the computational burdens of his direct method. This in itself demonstrates the work's honesty and rigor. The treatise fulfilled its own claims with remarkable fidelity, establishing analytical mechanics as the new dominant framework and providing the solid foundation upon which the grand edifices of Lagrange, Laplace, and Hamilton would later be built.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.